let's return to our conversation about Ramsey theory to try to find R24. So remember, when we try to find the Ramsey number R24, what we're looking for is the smallest n such that any two coloring of the edges of Kn, right, coloring the edges of Kn, red or green, is guaranteed to contain either a red K2 graph or a green K4 graph. So we're looking for a green K4 or a red K2, and we want to be sure that every coloring of Kn is guaranteed to either contain a red K2 or a green K4. And just as a reminder, right, red K2 graph just looks like this. It's just two vertices with an edge between it. A K4 graph is going to look like four vertices with all edges between it, so it looks like a box like this. Okay, so we need to find the smallest such n. I'm just going to try guessing and checking for some small values of n, and I'm going to look for counterexamples. In other words, I'm going to look for, all right, let's start with n equals 2, because n equals 1 is sort of silly. I'm going to look for a coloring of K2 that does not contain a red K2 and does not contain a green K4. Well, clearly, I don't want to color this red edge red because then it would contain a K2. But if I colored it green, this contains neither a red K2 nor a green K4, which means this R24 is not going to be equal to 2. We found a counterexample. All right, let's think about when n is equal to 3. Well, similarly, I could choose to color this with all green edges. This graph contains neither a red K2 nor a green K4. Clearly, it doesn't have enough vertices to contain a green K4, and there's no red edges at all, so it doesn't contain a red K2, which means this R24 number is not going to be equal to 3. It's going to be bigger than 3. Okay? Well, what about n equals 4? All right. We could try to play around with it a little bit. Oops, K4 looks like this. And we're trying to color it in such a way that this coloring does not contain a red K2 and also does not contain a green K4. Well, if I don't want it to have a red K2, then I really can't use the color red at all, because as soon as I color one of these edges red, you're done, right? You're kind of sunk. You've already found a red K2 graph. But if I don't use red at all, then I would have to use 4 green. But once you use 4 green, then you certainly have a green K4 graph contained here, namely the entire thing itself. Right? So claim R24 is actually equal to 4. In other words, any two coloring of the edges of K4 must contain a red K2 as a subgraph or a green K4 as a subgraph. Why is that? If even a single edge is red, that single edge is your red K4 graph, red K2 subgraph. And if not, otherwise, all edges are green, and thus your entire graph contains, and actually is equal to, a green K4 subgraph. Okay, which means by this argument here, R24 actually has to be less than or equal to 4, but up here we saw by using counterexamples that it had to be greater than 3. So if it's greater than 3 and it's less than or equal to 4, then it's going to be equal to 4. So R24 we have found to be equal to 4. So for small values, we can compute these Ramsey numbers by hand. But even once it gets just a little bit bigger, like R55, it's a very tough one to do. So I'll only be asking you to play around with this for small values in the exercises. Okay, one last extension. Ramsey's theorem really extends to the infinite case, and in fact, this is pretty much what Ramsey had in mind when he was first developing these results. He was using it to help sort of guide some decidability problems in logic, which really deals with infinite sets rather than finite sets. And so the infinite version of Ramsey's theorem for pairs says that if G is a complete infinite graph with a vertex set xn, where n is a natural number, so essentially we're saying it's a graph with the natural numbers, many vertices, and every possible edge between them. And if we color the edges of G with the colors 1 through n, then there exists an infinite subset of those vertices, such that for every pair of vertices xi and xj in that infinite subset, xi and xj have the same color. We call this a homogeneous subset because every pair of vertices in this subset are colored the same, right? So just to give you a picture of what this looks like, and I can't draw the whole thing because it's infinite, but let's just look at the two-color case. So let's say we wanted to color this with some red and some green edges. Maybe I'll color this green, and this green. I'll color this green, and this green, and this green, and this green. And maybe I'll color all the rest of my edges red. Okay, so remember, Ramsey's theorem says this is going to be true even if you have n many colors. N could be a lot. You could have a million different colors. You'll still be able to find this infinite homogeneous subset. So I'm coloring all my other edges red, though. For this example, I'm just using 2 colors. Well, Ramsey's theorem in the infinite case says you can find an infinite subset of these vertices so that every edge connecting pairs of vertices in that subset are all the same color. They're either all green or they're all red. So I can't tell you what it is here because I've only listed 6 vertices, but maybe I can give you an example of a homogeneous subset. Something like, how about, oh no, I should think through this example a little bit carefully. Well, one homogeneous subset would be x3, x4, and x5 is a homogeneous subset because every pair of edges here has a green edge, right? x3, x4 is green, x3, x5 is green, and x4, x5 is green. I couldn't add in x1 to this set and still be homogeneous because x1, x3 would be red, so that wouldn't work. And I couldn't add x2 because x2, x3 is red, and I couldn't add x6 because x5, x6 is red, right? But this is a small homogeneous subset. The infinite Ramsey's theorem says if we continued this for infinitely many vertices, you're guaranteed to get a homogeneous infinite subset. And you can see that it's sort of hard to find that, right? And again, infinite Ramsey's theorem doesn't necessarily tell you how to find it, it just says that it exists. And so this sort of leads to a really interesting question in logic and just how hard it is to find these particular kinds of Ramsey numbers. And you can also imagine that if we add more colors, it makes it even more complicated. But it's a really rich area of study that people are still working on today and still trying to work on finding better bounds for these numbers.